My name is Mr. Kangas, and today we're going to be taking a look at Chapter 5, Section 6. And today, in particular, we're going to be taking a look at finding the LCM of monomials. So we're going to be adding some variables into the mix. But first, I want to briefly touch upon two things. In the previous video, we learned how to find the least common multiple of two numbers. You will also be asked in the next section to find the lowest or least common denominator of fractions. If you want to find the lowest common denominator of fractions, that is the same thing as saying you want to find the LCM of the two denominators. So when I have 4/8 plus 2/18, if I want to find a common denominator, or the lowest common denominator, I would have to find the LCM of both 8 and 18. They're the same exact thing. LCD and LCM are actually the same thing. The only difference between them is you can find the LCM of any two numbers in the world, whereas LCD is specifically referring to the LCM of two denominators in two fractions. Whereas LCM, you don't have to be referring to the denominators of two fractions, you can just be referring to the numbers 8 and 18, not in fraction form. So if you want to find the lowest common denominator, just look for the LCM. If you just want to find a common denominator, because you don't always have to find the lowest common denominator to add two fractions, you could just, an easy way to find a common denominator that's quick, is just multiply the two denominators together, and that will be a common denominator. But we'll discuss that more in the next chapter. The other thing I wanted to discuss is the way I have shown you how to find LCM works doesn't necessarily make sense. I will be making a video on that, and a video will be up on that shortly, but I will not be putting it up right away. So if there isn't a video up presently when you go to the website on why LCM works and you're curious, just be patient, and I will get a video up when I have the time. So today we're going to be taking a look at finding the LCM of monomials. So if I have 18xy squared and I have 10y, how do I find the LCM of these two monomials? It's going to be the same, pretty much the same exact process as finding the LCM of two numbers. The only difference is we're going to end up with some variables in the end, and I'll explain how that works. The variable part actually isn't that difficult. So to start, if I have 18xy squared and 10y, I'm actually going to start the same way I do with LCM normally. So I'm going to find the prime factorization of 18 and the prime factorization of 10. So the prime factorization of 18, we can break that down. 9 times 2, 3 times 3. So the prime factorization of 18 is actually 3 times 3 times 2. The prime factorization of 18xy squared would actually be times x times y times y. So the only difference here is I've written out the variables that are being multiplied as well, because if you recall correctly, this means 18 times x times y squared. And y squared actually means y times y. It means you're multiplying two y's together. Now, I can't find the prime factorization of a number I don't know, so if it's just an x, I write an x down. I know that x is a factor of this monomial up here. I don't know if it's a prime factor, but I do know it's a factor, so I'm going to write it down as that. y squared written out, the factors of y squared are actually y and y. If I do y times y, it's the same thing as y squared. So all we've done to find prime factorization of this monomial is we found the prime factorization of the number itself, and you're going to find that this is a common theme with monomials. You're actually typically working with the numbers by themselves and then with the variables by themselves after. You don't very often work with them both together at the same time. You can separate them because this technically, like I said, it means 18 times x times y squared. They're not necessarily connected. They will end up getting you one number in the end when you multiply them all together, and that way they're connected, but you don't have to treat them as one number right now. You can treat them as pieces. So we found the prime factorization of the 18 to be 3 times 3 times 2. Then we did times x times y times y. So the variable part wasn't that hard. All we did basically was drop the variables down. If the variables have an exponent on them, we expand it. Instead of writing y squared, we do y times y. So now we're going to move on to the 10y. 10 can be broken down into 5 times 2. That's all we got. So I'm going to do 5 times 2. That's my prime factorization of 10 times y. So here's the prime factorization of 10y. Here's the prime factorization of 18xy squared. So if I want to find the prime factorization of these two monomials, just as I did with regular numbers, I'm going to circle what they have in common. So I can see that they share a 2, and I can see that they share a y. Now if you can, as you're writing out the prime factorizations, if you can line up the numbers they have in common, it makes things a little easier. It's not always possible without a little bit of extra thinking. If you're okay with doing what I just did, then do it that way. If you want to line them up, so put the 2 underneath the 2, the y underneath the other y, you can do that. So for example, what I might have done is I write out the prime factorization of 18xy squared. And when I find out the prime factorization of 10y, I can write it in accordingly. I see there are no other 5, so I'll just put the 5 down. I see there's a 2 over here, so I'll put a 2 over there. I see there's a y over here, so I'll put the y over there. At which point, I can clearly see the 2 and the y that they share in common. So just like with LCM of regular numbers, we're going to cross off either the top or the bottom set of numbers that they share in common, which in this case are 2 and y. So I typically cross off the bottom. It's good just to get into a habit, either choose the top or the bottom. I always do the bottom set. And then what you're left with, you multiply together, and that will be your answer. So 3 times 3 is 9, times 2 is 18. 18 times 5 is 90. There's nothing else to multiply x by, there's just one x, so we leave it as 1x. We have 2 y's, so we can write that as y squared. That would be our LCM of these two monomials. So in the end, really the only extra steps you had to do was in writing out the prime factorization. You just have to write the variables out. And when we went to find the LCM, so let me back up there, I'm sorry about that. So to find the only difference there was in finding LCM of monomials compared to finding LCM of numbers is that with the variables, we had to write them out in the prime factorization. We didn't really have to do a whole lot with them. We just wrote them out. And with the, when you found the actual LCM, so after you crossed out what they had in common and multiplied everything together, essentially you just ended up having to write in the variables that were left over. If you have two or more of the same variable, it's typically you put the exponent. So if you have a y and a y, so if you have two y's, you write y squared. And that's about all there is to LCM of that's all there is to LCM of monomials. Tune into the next video on Chapter 5, Section 7, adding and subtracting unlike fractions, or Chapter 5, Section 8.